Hello students, welcome to the third lecture of this course. We will continue to discuss basics of the spectroscopy. So, in the last lecture we discussed that electromagnetic radiation can behave as both wave and particle. So, it has dual character. Similarly, we looked at the materials, and what we found out is that small molecules or small particles can act as a wave. Small particles can act as a wave. So, in this lecture, what we are going to discuss is about your color of the molecules or color of the different objects. And we know that nature around us is colorful. If you look around, you will see objects of different colors. For example, cherries are red and blueberries are blue. So, we need to understand why cherry looks red or blueberry looks blue. So, similarly, if you look at the stars in the night, some of them will look red and some of them will look blue. Now, question is why? So, scientists during early days also were anxious to know the answer of this. As such, light itself has no inherent color. So, our perception of this different color is due to the interaction of light with the matter. So, the color which we perceive is basically due to interaction of light which has no inherent color with the matter. So, the way electromagnetic radiation can interact with matter is manifold. So, if electromagnetic radiation falls on a matter, what can happen is a part of it can be absorbed, or most of them can be absorbed. After absorption, what can happen is that material will re-emit the electromagnetic radiation, and this process is called emission. The second thing which can happen is that once a part of light gets absorbed, the rest of them will get transmitted. Again, the third scenario is that after interaction of EMR with matter, the electromagnetic radiation can get reflected, and reflection is when the angle of incident with normal is equal to this angle. When electromagnetic radiation falls on the matter, it can undergo refraction. It means it can undergo bending. And the other scenario is after the interaction of electromagnetic radiation with the matter, light can be scattered by matter, and scattering can be in all directions. So, this is 5 most common way in which electromagnetic radiation interacts with matter. So, it can get absorbed, it can emit the absorbed light, After the absorption, a part of light can get transmitted, electromagnetic radiation can get reflected, it can undergo refraction or it can undergo scattering. So, what is color? Color of an object we see is due to wavelengths that reach our eyes, reflected, transmitted, emitted or scattered. So, the color which we perceive is due to the wavelength of the light which reaches our eyes, either due to reflection, due to transmission, due to emission or due to scattering. Our eye acts as an optical instrument. They are sensitive to visible part of the electromagnetic radiation. So, from wavelength of 380 nanometer to 710 nanometer. The wavelength of light which we receive is perceived as color. Now, eye has different parts. Eye has different parts. You have cornea, you have iris, a lens, this is vitreous humor and there is a retina, and this is your optical nerve. These are the few parts of our eye. As other optical instruments require, eye has an image forming surface and this is called cornea. This is called cornea. And we also have a detector which is basically retina. This yellow one is your retina. So, the retina is photosensitive tissue of the eye, and this retina has two types of receptor, rods and cones. You can see here these are the rods and these three are cones. Rods are numerous and adapted to low intensity light, and that is why they are better suited for the night vision. But rhodopsin, which is contained in rod cells, bleaches rapidly in the bright light, and so rods are not active in the presence of light. On the other hand, cones are suited for daylight vision, and cones have different kind of color pigments. They have three color pigments. Here you can see these two are blue, these two are green and these two are red. So, most humans have three color pigment. That may not be true with the animals or other species, but humans have three color of pigments. Some of human may have two color pigments, and that may lead to your color blindness. So, when light falls on a particular wavelength falls on our eye, it can stimulate these three cones to different extent, and depending on percentage stimulation of these cones, or you can perceive the color of an object, and this can be from this region to this region. So, what I mean by this is, when you see a leaf, it looks green. Now, what is the reason for it being green is, when electromagnetic radiation, for example from sun, falls on a leaf, it reflects green color or light of green wavelength, light of green wavelength. When it reaches our eye, the different cones associated with retina gets stimulated to different extent. For example, when green light reaches our eye, the green cones are stimulated to 90% and similarly a bit of red cones are also stimulated, and when it happens you see a green color, So, based on percentage or based on extent of stimulation of these three cones, we see color or we see object of different color. So, in this case it is the reflected light which reaches our eye. Here we see the leaf green, since when light interacts with leaf, a green part of it is reflected to our eyes, and that is the reason why leaf looks green. Now, you must have seen the rays from sun or rays from a electric bulb. So, this is basically a part of what we know as emission spectrum. So, what happens is that if you look at the light coming from sun, they are example of continuous spectrum. So, here we are looking at emitted light. Emitted light can be of different types. One is continuous spectrum, which is because of continuous spectrum, which means that sun is emitting the radiation of all colors. Similarly, your electric bulb does same thing, and when you receive light of every wavelength, then you know that you are looking at continuous spectrum. On the other hand, if you look at the lamps, for example zinc lamp and rubidium lamp or mercury sulfide lamp, you will see different color. They are emitting wavelength of a particular color. So, here emission is not a collection of every wavelength, but one wavelength or a very narrow range of wavelength. Similarly, if you look at the LED lights, they also emit light of a certain wavelength, and this kind of source are example of source for discrete spectrum. Discrete means particular wavelength. Discrete means your emission of a particular wavelength, whereas continuous spectrum means you are looking at a light which is a combination of almost every wavelength. Color of an object can be due to absorption and transmission. So, a gem, this particular gem looks red because it transmits the red color. So, when incident light or light is incident on this kind of gem, it transmits only the red color, and that is why it looks red. Other colors are absorbed. The color can also be due to a scattered light. So, for example, from the sunlight we get a continuous spectrum. What does that mean is we are getting the waves of whole range of wavelengths from the sun. When sunlight passes through atmosphere, there are several particles in the atmosphere, and what they do is they scatter wavelengths or scatter waves of different wavelengths. And waves of different wavelengths are scattered to different extent, extent, and that is why some of them will reach our eye, some of them may not reach our eye. A particular wavelength, if suppose a wave of blue wavelength or suppose blue light reaches our eye, so then we will see object as blue, or we will see sky as blue. So, during the different part of the day, the sun or the sky will look different, because we are receiving the light or receiving a different kind of light during different time of the day. For example, the atmosphere scatters blue light more effectively than red light, hence mostly blue light reaches our eyes when we look at the sky. So, during the daytime, the blue light is scattered more effectively than red light, and since during the daytime it is the scattered light which reaches our eye, and so we see sky blue. So, here is your scattering shown in the figure, and you can look that blue is scattered more, whereas red is scattered less, and the blue one reaches our eye during the daytime, and that is why during the daytime the sky looks blue. On the other hand, if you look at the sun or sky when sun is setting or when sun is rising, what will happen is you are not looking at the scattered eye, or you can tell that it is not the scattered light which is reaching our eye, it is unscattered light which is reaching our eye. And so, during the sunset or sunrise, sun looks red. So, again the atmosphere scatters blue light more effectively than red light, hence during the sunset unscattered light reaches our eye, and that is why your sun looks red or sky looks red. So, this is about why we perceive a particular color of an object. For example, apple are red, blueberries are blue. This is because the light which is reaching our eye is not the light itself, it is the light which is reflected, refracted, transmitted or scattered by an object. So, we can utilize this, or what we can do is, instead of eye, we can observe wavelength, frequency absorbed, emitted, transmitted or scattered by an object, atom, molecule by placing a detector in appropriate direction, and what we will get is a spectrum. So, instead of eye, wavelength, frequency absorbed, emitted, transmitted or scattered by an object, atom, molecule can be observed by placing a detector in appropriate direction. So, what I mean by that is, so suppose we are going to look at transmitted light. In that case, what we need to do is, if you want to see the transmitted light, what we can do is, you can put a detector in the line with light source and sample. So, this is line between light source and sample, and in this line itself you put a detector. Then you can look at the transmitted light. But if you want to look at emitted light, what we need to do is that if you take this line between light source and sample, you need to put your detector perpendicular to this line. So, by putting detectors at appropriate place, you can see the transmitted light or emitted light. So, based on the interaction between electromagnetic radiation and object, you can think of different type of spectroscopy: absorption spectroscopy, transmission spectroscopy, emission spectroscopy, reflection spectroscopy, refraction spectroscopy, scattering spectroscopy, diffraction spectroscopy, optical radiation spectroscopy, or interference spectroscopy. So, several kind of spectroscopy is possible. Depending on the interaction of your electromagnetic radiation with an object. Each of these spectroscopy can give you a particular kind of information, and if you combine the information from different kind of spectroscopy, you can completely analyze a particular sample. Now, next topic is quantization of energy, and this is very important concept in the spectroscopy. So, if you look at the spectrum observed from different sources, particularly emission spectrum, you will either see a continuous spectrum in which radiation is distributed over all frequency, not just a few specific frequency ranges. So, you can see it is going from the red to blue. So, basically radiation is distributed over all frequency in continuous spectrum. For example, if you see the emitted light from the sun, it is an example of a continuous spectrum. So, when we get continuous spectrum, when we heat a body or any hot body produces a continuous spectrum. So, if it is hot enough, it will look like something like this. So, you are seeing from violet to red, light of every frequency, and digitally how it will look like is this. So, this is your intensity versus wavelength, and you can see that at every wavelength you can see intensity. It may be low intensity, high intensity, but at every wavelength or light emitted consists of every wavelength, and that kind of a spectrum is called continuous spectrum. In the line spectrum, now you can see that there are lines. You do not see the light of every wavelength. So, when you can see this kind of a spectra, so pattern of bright spectral lines is generally produced by an element. So, an element will show pattern of, if you hit an element, then you can see pattern of bright spectral lines, and that is known as line spectra. So, when you can see line spectrum, one is by hitting an element, another by applying heat to a gas, and that will produce an emission line spectrum like this, where you can see that only light of this particular wavelength is observed. If you like to see it digitally, how does it look like? This will look like this. So, you can see intensity is, you can see intensity at some particular wavelength, not at every wavelength. And so, there are two different kind of things which I already talked, can show you emission lines. One is your gases, when they are heated, they will show the emission lines. Similarly, when you heat elements, you will see emission lines. And interesting thing about emission lines of an element is, every element has different line spectrum, or they emit light of different wavelengths, and this can be used to know whether particular element exists in the sample or not. So, for example, hydrogen will show you this kind of spectrum, whereas sodium will show you this kind of spectrum. So, different element has different emission lines, and that can be used as fingerprint to detect the atoms or elements. What is the absorption spectroscopy? So, absorption spectroscopy is basically pattern of dark spectral lines where light within a range of narrow frequency ranges has been removed. So, we looked at two kinds of emission spectroscopy. Now, this is your absorption spectroscopy. What is happening here is light of particular wavelength is getting absorbed, and that is why those lines or light of those frequency has been removed from the light. And when we can see that, any gas placed between a continuous spectrum and the observer will produce a absorption line spectrum like this. So, for example, if you place a gas between sun and us, you can see the absorption line spectrum, and absorption line spectrum looks like this, and digitally it will look like this. So, you can see that the line here, the light is missing. So, light of these particular wavelengths are missing because they are absorbed by the sample. So, if you look at atomic and molecular spectra, absorption and emission of electromagnetic radiation by atoms or molecules occur only at discrete energy value. So, if you look at the line spectrum, you will see that only emission is happening of electromagnetic radiation of only discrete energy value, or emission is of a particular wavelength, not emission is not like the emission from the sun. Similarly, if you look at absorption spectra, absorption spectra of a gas, you will only see that absorption is happening of particular wavelength. What does that mean is that your absorption emission of electromagnetic radiation occur only at discrete energy value, and classical physics won't predict that. It will predict absorption or emission at all energy levels at all energies. And so what we have seen that in emission spectra, particularly in line spectra, if you take a hot gas, it will show you a line emission spectra, and if you take a light and you pass through cold gas, what you will look at absorption spectra. In both these cases, line spectrum and absorption spectrum, the absorption and emission happens at discrete energy values. So emission happens at this value, emission happens at this value, emission happens at this value, not all the values. Similarly, absorption happens at this value, absorption happens at this value, these two values, this and this, not at all values. And that can not be explained by classical physics. This observation can be explained only on the basis of quantization of energy. So what I am going to discuss now, how the science about quantization of energy evolved. So people started to study the black body radiation. So first we should know what is a black body. A black body is a theoretical or model body which absorbs all radiation falling on it, reflecting or transmitting none. So whatever falls on this, it absorbs everyone. It absorbs waves of every wavelength. It does not transmit anything. This is also an object which is perfect emitter of radiation over all length, radiation over all wavelength. So it is a perfect absorber, it is a perfect emitter. A hot body emits electromagnetic radiation of varying frequency depending on the nature of object and its temperature. As the temperature increases, the peak wavelength emitted by the black body decreases. What does that mean is, if we increase the temperature, the emission will be of higher frequency. Emission by the black body will be of higher frequency light. As the temperature increases, the total energy emitted also increases. What does that mean is, not only frequency is increasing with the temperature, the energy of emitted light is also increasing. So as temperature increases, both energy and frequency of emitted light increases. So this is called Planck spectrum. Here we will show you. Now look at this, that when you hit an object at 300 K, it is not showing any color because it does not fall in your visible light region. At 1000 K, it begins to glow deep red, and you can see that this part of at this frequency, you can see it is overlapping with the red region. At 4000 K, the maxima is at red, and so it becomes red hot. At 4000 K, you can see maxima is here, and if you go to 7000 K, maxima covers all this wavelength in the visible region, and that is why it looks white hot, white hot. So as object is heated, radiation it emits peaks at higher and higher frequency. higher and higher frequency. An opaque object emits electromagnetic radiation according to its temperature. If you heat a iron rod, if it is hot enough, it will first glow deep red like this. If you heat more, it will glow as a reddish orange, and if you make it even hotter, then it will glow like a yellowish white. Similarly, if you look at the sky in the night time, it will show stars of different color, and that is because of its temperature. So, red stars are relatively cool. Yellow star such as our sun is hotter, and a blue star is very hot. So, red star temperature is around 3000 degrees Celsius. Your yellow star like our sun is 6000 degrees Celsius, and a blue white star is at 40,000 degrees Celsius. So, because of temperature, a particular star will look red or blue. So, it is the temperature which decides color of the stars. Now, let us understand this, what is happening. We know that atoms are in motion, and everything is composed of atoms which are constantly in motion. The hotter the object, the faster the average motion of atoms. So, if you compare between a hotter object and cooler object, in the hotter objects, the molecules are in faster motion. As the atom collide due to motion, collision gives off energy, and the energy is emitted as light. So, the hotter the object, the faster the average atom, and more energetic the average collision. Faster the atom, the more collision there are, and the emitted light will be of higher energy. So, as you increase the temperature, motion of atoms increases, there are more collisions, and the light emitted is of higher frequency. So, the more energetic the average collision is, bluer the average light that is given off, since E is equal to Sc by lambda. The more collision that occur, the more light that is given off per surface area. So, this explains you why with increase in temperature, both frequency and intensity of the emitted light increases. So, two things, hotter is bluer and hotter is brighter. These are the observed phenomena from black body radiation. So, people tried to explain this in terms of several laws, and there are three very important laws which are used to explain this phenomena. One is Planck's law of black body radiation, the second is Wien's displacement law, and third is Stephan-Boltzmann law. So, first attempt or good attempt was made by Rayleigh-Jeans. They calculated energy density per unit frequency, and according to this law, this energy density is given by this expression 8 pi nu square by Cq, an average value of E. And according to classical physics, this average value of E is equal to kT. Average value of E is kT. When you apply this classical physics, what you will get is this kind of your prediction. So, radiation, the energy of radiation versus wavelength should look like this if classical physics holds true. What classical physics predict that even relatively cool objects should radiate in UV and visible region, and in fact classical physics predicts that there would be no darkness, but that is not true. The observed one is this one, that if you, so this is your increasing wavelength, and if you go in this direction you have increasing frequency. So, with the increasing frequency you can see here that it goes initially up and then it goes down, and that is quite different from the curve explained on the classical physics. This difference is known as the ultraviolet catastrophe. Ultraviolet catastrophe. The difference in the experimental and the curve obtained based on your classical physics was explained by Max Planck. Max Planck explained this deviation by assuming that the energies of the oscillation of electrons which give rise to radiation must be proportional to integral multiple of the frequency E is equal to nh nu. This recognition that energy changes in discrete quanta at atomic level marked the beginning of quantum mechanics, and Planck won the Nobel Prize in Physics in 1918. So, what was the Planck concept? That average energy per mode or quantum is the energy of quantum times the probability it will be occupied, and the value of E is now no longer equal to kT, it is basically h nu divided by exponential h nu by kT minus 1. And when he used this formula, he was able to predict the experimental or able to explain the experimental observation. The Wien displacement law tells you about how temperature affect the F maximum or frequency of the peak of the emission maximum. As the temperature of body increases, the wavelength at the emission peak decreases, wavelength of emission peak decreases and frequency of emission peak increases, and there is basically the proportionality relation between frequency and temperature, and that is known as Wien's displacement law. Stephen Boltzmann law talked about intensity, that total energy emitted is proportional to temperature power 4. So, the black body radiation curve shape is explained by, the shape of black body radiation curve is explained by Planck's law. The temperature dependent on frequency dependent on temperature is explained by your Wien's displacement law, and energy dependence on temperature is explained by Stephen Boltzmann law. Intensity at all wavelength increases as the temperature of black body increases, and the total energy being radiated increases rapidly as the temperature increases. We have seen that Rayleigh-Jean's law works for lower frequency, but it diverges at higher frequency, and divergence for higher frequency is called the ultraviolet catastrophe. We already discussed these things. The next observation is about the heat capacity of monoatomic solids. Classical physics predicts a constant value of 25 joule per Kelvin per mole for the molar heat capacity of monoatomic solids. Whereas, when we do experiment at low temperature, what we will observe that molar heat capacity approaches 0 when temperature approaches 0. So, here is a plot between Cv by 3 Nk and Kt by epsilon. Classical physics predict that Cv by 3 Nk should have value of 1. But when you do experiment at higher temperature and Kt by E is high, the classical physics prediction is right, but at low temperature it fails. At low temperature it fails. In fact, your heat capacity of monoatomic solid approaches 0 at low temperature. This experimental observation can again be explained based on Planck's theory. Assumption of discrete energy value again led to a model that matched the experimental observation. So, based on the explanation for black body radiation and molar heat capacity, also the discrete spectrum observed in case of atoms led to the concept of quantization of energy. So, in the black body radiation we saw how we can explain the ultraviolet catastrophe by taking discrete value of energy. Similarly, molar heat capacity of monoatomic gases at low temperature can be explained by taking your discrete value of energy levels. Similarly, transition between atoms can also be explained, or emission spectrum of atom can also be explained on the discrete value of energy levels. If suppose there are discrete value of energy level, then you can explain emission or absorption of particular wavelength. If suppose these two energy level exist, then if there is absorption, it will absorb wavelength corresponding to this delta E value, and the relationship between delta E and lambda is given by this. If there is emission from this level to this level, then again you can see the emission of the wavelength corresponding to this delta E value. And if suppose the energy difference is higher, then lambda will be smaller. If the energy difference is smaller, then lambda will be higher. So, on absorption of light of energy delta E, species go to higher energy level, and if there is a discrete value, this delta E will be fixed, and you will get, or that sample will absorb lambda of this wavelength. So, in this relation, h is Planck's constant, nu is frequency, c is velocity of light, and lambda is wavelength of light. So, in this lecture we have discussed about quantization of energy, and concept of quantization of energy is important because this quantization of energy led to development of quantum chemistry, and quantum chemistry is quite important to understand the basics of spectroscopy. So, I will stop here and thank you for listening. I would like to acknowledge these books which I am referring regularly to make slides, and I have taken lot of figures, animation from the web sources, and I have tried to acknowledge them, and please let us know if there is a omission, and thank you again for listening, and see you in the next lecture. Thank you. Bye.